Hello guys, and welcome to another video. This time we're going to talk about the Casio Loopy, which was an old Japanese console released in 1995. It was meant to be targeted at girls. Well, it was not actually the initial objective of the console. They were just trying to make a console for kids, I believe. But then they targeted it for girls, and I believe it was a huge mistake. And you will see maybe why. Uh, yeah, the hardware itself, it's not hugely impressive, especially by 1995. It's perhaps on par at best or slightly worse than the 32X. So not exactly it's not exactly powerful by any means. It's I would say it's more like a turbocharged Super Nintendo. And yeah, we're going to talk about the technical specs of it and a technical overview of the hardware itself. So let's get started. It hardware only has one controller port, which is an odd decision given the target demographics. Uh, One printer slot, which is used to print stickers. That's the main gimmick of the console. Composite output only, although the console itself actually outputs analog RGB through its VDP chip, and then it encodes that with a Sony chip to composite. DC output, so up to 24 volts and as low as 7 volts. Although I only tried as low as 9 volts with a USB-C cable that I bought on AliExpress. It worked just fine. And it was consuming about 3.5 watts when not printing. When it is printing, I believe it would go a lot higher, like maybe 7, 8 watts, but I cannot say for sure. There's also a slider for changing the contrast. Now, it's for changing the contrast of the printer, not the composite output. And there's also like a huge eject button. It's comically large. Like, it's kind of hilarious, actually. There's also a reset button, and yeah, and a power button. It's actually a slider. That's really all there is to it. And a cartridge slot, of course, which for the cartridge slot, it's up to 4 megabytes, just like the Mega Drive. If you want to go beyond that, you will need to do bank switching. As far as I know, there were no games that made use of bank switching. All games were either 2 megabytes, 3 megabytes, or 4 megabytes. You can go lower, of course, but yeah, that's it. So about the technical specs, the CPU, it is indeed the SuperH1, more specifically the SH7021. This variant has 1 kilobyte of on-chip cache, which I'll talk about a bit later. Wikipedia got this wrong about the RAM. So actually for the RAM, it's 512 kilobytes of main RAM plus 128 kilobytes of VDP. I don't know where they got the 1 megabyte number from. I believe they confused the sound sample as RAM. But then again, they mentioned that it had like 2 megabytes of ROM. That's also wrong. So yeah, for the ROM, it's 512 kilobytes of ROM, which are solely dedicated for sound samples. That's quite large. And 32 kilobytes of mass ROM inside of the CPU for the BIOS. So when the CPU resets, the master vectors, the master reset vector, it jumps back to the address 0, which is where the mass ROM is stored. I believe that's how it works. It works something like that on the Sega Saturn, which used an SH2. I should also mention that the SH1, although it was only used on the Casio Loopy as a main CPU, the Saturn used the SH1 for the CD drive as well, which I believe is a bit overkill, to be honest, but it was mostly used for asynchronous loading and stuff. The VDP chip, it's also capable of 512 colors. Now, this is a bit, I was confused at first, but basically you have 256 colors for backgrounds and 256 colors for sprites. So yeah, that's how it works. And finally, we have 4 channels of PCM sound, but the samples are hard-coded. You cannot use your own samples due to how they designed the hardware. You can you can make sound effects using the samples that are hard coded in the ROM, but you cannot upload your own PCM samples. There could be a way to bypass that, but the hardware is so woefully undocumented that people don't know basically. So yeah, this is the PCB of the hardware. So as you can see, the VDP chip, well, the video chip, the RH 7500, it's quite large. Like the PS1 for like the GTE, it was this large as well, and it was a lot more capable than this video chip was. The CPU is actually quite small by comparison. And as you can see, I showed you where the RAM and VRAM is. For the VRAM, it's only like 128 kilobytes, and that's all you get. For the RAM, it's 512 kilobytes of RAM. So it's actually 256 and then 256 so you get the amount of 512 kilobytes. Now for the sound chip, this is like an overkill setup for the sound chip. So there's a support chip for the sound chip, and then it then talks to the main sound chip. And just look at the size of these things. I don't think it was the most clever design for a console. Like they could have done it a lot more cheaper. Like the eject button was just comically large. Like the too many chips, to be honest. It could do, like for the games that they did on this, they could just have like a simple frame buffer and then the CPU. And then for the sound chip, they could use like something that's like the Sony sound chip that they use on the Super Nintendo, not this setup. And that would have been a lot more capable because the sound chip, it ends up being worse than the Super Nintendo. Even though the sound samples, they may sound nice, yeah, what a waste. And of course, they have to waste a bunch of money on the ROM, which is 512, and you cannot upload your own samples. I don't know what the hell Casio was thinking when they made this hardware. They could have stored the samples on the game cartridge themselves and then lower the cost of the console. But I don't know what the fuck they were thinking. Obviously, when they switched the market to little girls and stuff, they didn't know what they were doing. Anyway, let's talk about the main attraction, I would say, the CPU. This is a 32-bit CPU, and it's clocked at 16 megahertz. Now, this doesn't seem like very powerful, especially when you compare it to like the 32X and stuff. But compared to something like the 3DO, it's actually a lot faster than the main CPU of the 3DO. That's because on the 3DO, each instructions, they could take like 5 cycles, 10 cycles, even 20 cycles. On the Super H, most instructions, most operations, if you do it well, they can take like as little as 1 or 3 cycles. There are even so-called 0 cycle instructions. So how it's done, it's basically, since each instruction is 16 bits, and their architecture is itself 32 bits, then you can do so-called like 0 cycle stuff. There was also the stuff with the multiplier, which is on which you can do like you can run like your divider and then do a bunch of stuff in the meantime. That's also a thing. I know it was a thing on the Super H2. I'm not too sure about the Super H1 because it's a bit more limited, even though it's quite the same. And just like the Super H2, it also has a DMA controller engine as well. So it has a bunch of DMA channels, so you can tell it the source, destination, the size, and then it will do the job for you. This is not well emulated right now for the Casio Loopy. They only emulate it like partially, but and it's a bit confusing how to use it. And it also seems like the addresses that some people say it is for the Casio Loopy are actually incorrect. Now the games, how they use DMA, there's a BIOS DMA function routine that they can use. So they set up a DMA list, and then they just let the BIOS ROM deal with that because they have routines for that. Uh, Another difference with this SuperH2, just like on the Saturn or 32X, there's no instruction cache or data cache. Instead, there's 1 kilobyte of on-chip RAM. And how this works is it's basically like the PS1 does. So on the PS1, what Sony did was instead of having the D cache, they used it as a scratch pad, so fast RAM, and basically you can store like a lookup table in the fast RAM, and then that would basically avoid the penalty with like wait states when it comes to RAM and stuff because it's super fast. I'm not a huge fan of that, especially on the PS1. I believe they should have made this a toggle. Obviously, on the Casio Loopy, that's not an option because the CPU is simply not capable. It only has 1 kilobyte of on-chip RAM. I don't even know its location, by the way. So right now it's useless. You have to specifically target the on-chip RAM to do stuff with it. Otherwise, it's not a lot of storage, 1 kilobyte either. So it might as well not be there, but I know I'm a bit difficult. Now, compared to the SH2, there's also a lack of 16 bits multiplication, and obviously the lower clock speed. There are also other differences, but stuff about the 16 bits multiplier, that was Sega had an issue with this processor when they showed the SuperH1 to Sega. They complained about the fact that it could only do like 16 bits by 16 bits multiplications. They needed like 32 bits multiplications. So for the SuperH2, they added that. They also added multi-processor support, which was not on the SuperH1, as you can see. Okay, let's talk about the VDP chip, also called the Casio RH 7500. This is the big chip that you saw on the motherboard. It's locked at 21 megahertz. It accepts 16 bits writes. If you attempt to do a 32-bit writes, they will get halved instead. They will still work though. The graphics, I would say they're superior to the Super Nintendo, but it's not that much superior. The main difference is the fact that you can do more colors on screen at once without special trickery. And the it can support multiple backgrounds, although that's only true if you use the 4BPP modes, because in 8-bit modes there's not enough space in VRAM for multiple backgrounds. So yeah, and there's also the stuff with sprites and etc. Uh, it can do bitmap graphics though. That's the main attraction to me, at least. And games use the bitmap graphics to do stuff like, I wouldn't say special effects. But they can do you can do a raycaster on the Casio Loopy, for example. That's what I showed you before, just like you can do on the PCFX, but it's a lot faster on the Casio Loopy. And you can also make use of DMA on the Casio Loopy as well. And there's even a routine that you can talk to the VDP to do some fast clearing. And you can do it in only like at the cost of a few CPU cycles. Unfortunately, when I tried to do that and then draw stuff through the VDP, there was a bit of flickering. So yeah, I should also mention that at 8 BPP, it can do 256 by 512 in terms of resolution. So in theory, you can do double buffering. So you can use the second half to store like your non-active page, then the other half for your active page, the one that you. So basically, you draw to the unseen page, then you flip, then you continue the cycle. And the palette is actually RGB 555. It's not BGR 555 like on the 32X or the Game Boy Advance, which is another quirk of the hardware, interestingly enough. Uh, Now, this may like hugely impressive, but in reality, most of the Casio Loopy games, they were going for like that 2D look. So they end up not looking much better than Super Nintendo. In fact, I would suspect that on the Super Nintendo, you could do quite similar stuff, especially if you have a Super Nintendo with a Super FX chip. That would be essentially the same as this. The only difference would be like the CPU is much faster, but other than that, yeah. So the Micro PD9 37, also known as the NEC CDT 109, that's the sound chip that we talked about on the motherboard. It is sample based, just like the Amiga and Super Nintendo. It's 12 bits PCM. However, the samples, as I mentioned earlier, they are hard coded in ROM, and there are just a little over 100 instruments that you can use. And the BIOS has routines to play MIDI based tracks, and you can also define, like, as I said earlier, kind of like your own special sound effects, but they are still samples stored in ROM. So yeah, it's quite limited. So for example, here's a BIOS routine and its location, and yeah, you have a track list with all of your stored sound effects, and then you just tell it the index. And so I don't know why it cares about the track list or index, but it is what it is. I believe the sound state is for so the program knows if the sound is currently playing or not, but I don't know why it's a void. It's a bit confusing. Now let's talk about the BIOS ROM. Like the 512 kilobytes of ROM, that's actually for the sound samples for the actual BIOS ROM. That's the mass ROM in the CPU, which is 32 kilobytes. And that is why for a long time people actually struggle to dump the BIOS because it was just inside of the CPU. I believe what they did was kind of try to leak out the content of the BIOS. I forgot there's a program that you can use to dump your Casio Loopy BIOS, and that's what you can use usually. This you can do the same for the sound samples though. That's kind of harder. And I mean, I showed you like one function for sound, but it also has other math function, mostly for multiply, divide. Uh, there was also some function related to plotting a pixel, drawing a line, and also initializing sound, music, and stuff. And also functions that seemingly are related to the printer. I believe you just send like a frame buffer, like or a line buffer to the BIOS routine that would then deal with the actual printing. Obviously, I cannot test that because I don't have a printer, but that's how it works. So yeah. Now, I want to show you the cube demo that I made on the Casio Loopy. It works kind of like the PCFX one, except for this one, of course, I actually did not do a 64 by 256. I just did like 120 by 112 resolution. Or actually, it was 120 by 120 or something like that. But yeah, it was basically half of the resolution of the Casio Loopy on both axes. And as you can see, compared to the PCFX demo, it runs a lot better. It's actually at 60 FPS. It would have been a lot faster if I could figure out how to do DMA on this hardware. And yeah, because we're still wasting a few CPU cycles on actually looping this stuff. And of course, because of the lack of an instruction cache, the actual loop for clearing like the frame buffer, it's only partially unrolled loop. It's still yeah, and I believe that executing code from ROM is slower than doing so from RAM. So if I try to unroll the loop and I don't make use of the on-chip cache, that yeah, it is a bit of a quirky CPU. On the SuperH2, that would be a lot easier, obviously, because you don't have to worry about that. The instruction cache will just be way faster to make use of that. But yeah, another demo that I want to show you. Well, obviously I showed you this one before, and this one, unlike the Q demo, it doesn't use like the 240 line mode. It uses the lower one, so 224 line mode. And after I upgraded the compiler and also made some other changes, the game finally works properly. So it's made by the dude who is total weirdo. I already talked about this in another video of mine. I'll not talk about more in depth about this guy. But yeah, I don't get like weird instruction errors either. I have yet to try this on real hardware, but I've made a build, a binary build, available for people that do want to try it on real hardware. And the SuperH CPU, I forgot to mention, it lives and dies by alignment. If you do not properly align CPU instructions or data, it's gonna crash. The behavior will be quite not very predictable, basically. It will be undefined behavior, so to speak. So yeah, if your compiler is not doing so already, make sure that the data is aligned by 4. And you know, it runs pretty smoothly, but it's actually on par with the PCFX. There are multiple reasons why, but the main one is just lack of instruction cache. The PCFX has 1 kilobytes of instruction cache, and this game has multiple loops. So because of that, it ends up being not much faster than the PCFX, even though the PCFX, well, yeah, basically. And it could have been a lot faster on the PCFX if I could figure out how to do background. The PCFX can actually upscale, well, not upscale, so to speak, but make the backgrounds twice as large or 4 times as large. So zooming, basically, so to speak. And obviously, Casio Loopy cannot do that. It's not very flexible. It just provides a bitmap, some sprites, tile-based graphics, and that's all there is to it. Obviously, I'm not making use of that at all. I'm just using it as a fast frame buffer. So kind of like what you would do on DOS with a VGA graphics card. And that's basically how I treat the Casio Loopy. Even for 2D games. I made a 2D game on the Casio Loopy, and I didn't bother with like the tile-based graphics, even though I could have saved a bunch of VRAM. I just did like frame buffer graphics, and I did not even use like the actual sprite hardware. I just did it that way. So yeah. So that's all there is to it for now. The hardware is still very much unknown. The stuff about DMA, the BIOS routines, the sound stuff, which only has been figured out. I also forgot to mention that for the actual game, that you know the stupid dog game that was on the Casio Loopy, you may have noticed the game has sound samples. So how does it do sound samples? There's an actual ADPCM chip on the cartridge itself. The hardware is capable of routing the audio to the composite outputs. So that's how the game achieves sound samples. It doesn't use the hardware at all. So thank you for watching and bye.